Okay, good morning. Nice to see all of you. We're still missing a few people. Well, let's begin with the teaser question. Let me bring it up. Okay, can you see my screen with the teaser question on it?
Now we can.
Okay, great. So let's see. Let's take a. So I don't like to actually. I've now decided not to take this polls where you can see each other's answers because then they are not independent events. But let me. I think some of you have responded in emails. How many of you responded? I know I saw a response from Brad and Saad. Anybody else responded? Can you quickly respond whether A is a superfluid or B is a superfluid? Quickly, can people respond? There are like 14 of you now here. So as I said, it's a light scattering experiment. You have some system, you shine light on it, light interacts with that matter and scatters, and you observe the scattered intensity. Okay?
This is in real space?
Well, it's light scattering. So you're detecting as a function of angle, right? So what happens,
Okay.
you
So
have
that's
light incident on a sample at some angle, it scatters, and then you look at that light as a function of angle, right? You're detecting photons. So that's the setup. It's what you would do in a crystal to see the structure of crystals. Okay, great. Let me see. Are people responding? Hi, guys. Respond. You just have to say A is this and B is this. It doesn't take very long.
I would think A has a lattice structure, so it looks like a Mott insulator, and B is like diffused, so the electrons are flowing or the atoms are flowing, so it looks like a superfluid or a BEC.
Okay, that sounds good. Brad, did you want to add to that? So let's see what's on the table. A, according to Nish, according to Brad, and according to Saad and Franz, A is Mott, B is superfluid. What would you say, Jay? You walked in early.
Yeah, I think A is a mod state, and,
Okay.
and B. I mean, so I remember, if I remember correctly, the BEC has a single peak at k is equal to 0. So in real space, it should be just a constant. So.
Right. Okay. It's great intuition, but the answer. That's why I'm so happy to hear this. The answer is that A is superfluid and B is the Mott. Okay, that's the answer. So let's see why. Okay, so this is why this is interesting. Now, a crystal, your intuition going in was very, very correct, that a crystal is an ordered array of atoms. A Mott also looks like an ordered array of atoms. But there's a very big difference between these two ordered arrays. Okay, so keep this question in mind and let's kind of go through some of the ideas again. So it's good to have this teaser because now, you'll be little more curious about what happened. Why did it go the other way? And the other thing that Jay brought up, which is a BEC is a zero momentum peak. And so if I'm saying that A is superfluid, this is actually a picture in momentum space. It is a picture looking at angles at which you get scattering. But that angle can be converted into momentum. If you remember, quite a while back, I talked about light scattering and critical opalescence. We looked at light scattering near a phase transition. And what we were able to capture were the fluctuations in light scattering. And it happened from, you came in with a light at say some momentum K, it scattered into another direction K prime. The energy didn't change, it was elastic scattering, but the angle changed. And by looking at different angles, we could look at the range over which there were fluctuations in the system. So that was critical opalescence. Very similar experiments are being done here. So in a crystal, if it was an ordered crystal of some matter, like say aluminum or sodium, you would get these Bragg peaks, exactly like what you see in a superfluid. Here, that A superfluid. Okay, so we have a couple of things to discuss. We want to discuss the difference between a crystal, a Mott state, a BEC with a momentum condensate at K equal to 0, and this object that I'm still calling a BEC, but which seems to have Bragg peaks at many values of K, not just K equal to 0. Okay, so that's the plan before us. Now, one quick question. When you see my screen, do you see the faces on the side as well? No, that's not blocking your view, right?
No, no.
Okay, good. I wasn't sure what gets projected. Okay, so let's start delving into this a little more. So today, what I would like to do is I want to do the following. Let me see, I think I need to stop sharing and start again because I changed my medium. Okay. So I'll briefly talk about phase coherence. Okay. So the short answer to why the Mott insulator, even though it looked like it was an ordered array, what it is not is phase coherent. You can think of at every site of that Mott array, there's a little phase, a rotating phase. And that phase is random from site to site. Okay? So in a superfluid, all the phases are aligned in the same direction. That's what phase coherence is. So you remember we talked about the order parameter. It was the expectation value of BI dagger or BI. This quantity is complex. It has a real part, an amplitude, and an angle, phase. So in a BEC, you not only have a finite magnitude, but you also have symmetry breaking, which picks a particular angle for these phases. Let's say theta equal to 0 coming at you. So now every site has the same angle. That's the superfluid. In a Mott, you have like fluctuating phases because it has a fixed number. It has a very ordered or real space orientation, but every site has an angle which is fluctuating. So when light shines on it with a certain phase, right? Phase means it has a certain wavelength. That can get shifted when it scatters And now you're looking at interference of all these scattered waves, and it ends up giving you a blob. We still have to understand why the superfluid gave this particular Bragg's peaks, and I'll come to that. But the critical difference is that the Mott insulator is phase incoherent. Okay, so I'm going to kind of go over that briefly, but I will make some recordings later over the weekend. This is really our last lecture. Also, I have posted some references for you to look at. There is a very nice and complete reference by Fisher and collaborators. And last time there was a question about RG in this model, and I won't be doing that. We can't get to it in such a short time, but those of you who are interested should look at that Fisher reference. I also posted some notes on boson coherent state path integral. I gave you the idea of the path integral, and I will post some more notes on this, or maybe a recording, but we will use it in the class in like a very dimensional analysis way to get some critical results. Okay, so back here, this is the teaser we had. That was the real space picture and the light scattering picture. And that's the fluctuating picture in real space and the light scattering picture. So we'll get into that. Okay. So let me come to this. So we have the definition of the superfluid phase. It's this, we are looking for this off diagonal long range order, right? And if N0 is finite, that tells us about the condensate density, the density of bosons that are in the zero momentum state. Because when we Fourier transform this, it does give a peak at k equal to 0. I will come to the other peaks later, but this behavior here would give a peak at k equal to 0. Right, just like that. Okay. Okay, now, so this is one, so, you know, last time there was a question, if the order parameter is complex, how do we measure it? So this is not quite measuring the whole complex order parameter, but it's measuring a consequence of that. So the consequence is that this operator AR has an expectation value with a phase theta at site 0 and the same theta at site R. You see, that was implicit in there being long range order. So that's how there was long range phase coherence, because the same theta was there at both sites. And that's why you got a e to the I theta times e to the minus I theta from the dagger, and it canceled out. So it canceled out, but it's very subtle. It canceled out because there was long range phase coherence at two very different sites. Any questions? Okay. Now, the other consequence of this complex phase is shows up in the response function, and I'm bringing it up again because it's always useful to see it again in a different context. So here in the superfluid, the system has broken continuous symmetry, and let's say it has picked all the spins to be up. Okay. You can measure the response of the function, and that means you have to perturb it somehow. So let's say you apply a twist in the boundary condition to the wave function, right? So you artificially apply a twist. And in an experiment, such a twist can be applied by rotating the system. We have talked about this before, the rotating bucket experiment for helium-4. And in these cold atomic gases, they use lasers to rotate, two lasers like a spoon. It's called a laser spoon. It's quite inventive. They use two lasers and they rotate the lasers, and that's essentially like applying this twisted boundary condition. So now the result of this twisted boundary condition is that the phases are not going to be all up everywhere and then the last spin will flip. It doesn't do that. That's a very high energy cost. Instead, every site twists just a little bit, accommodating ultimately a pi over 2 twist. Okay, so this is like a spin wave. Every site is twisting just a little bit, and ultimately the total twist ends up being whatever has been applied at the boundary. And clearly the energy must go up, and that increase in energy is a half rho s grad phi square. We saw such a term in our Landau theory as well. So the coefficient of grad phi, which is the relative twist between two sites, that coefficient is called the superfluid density or superfluid stiffness. And that quantity also measures superfluidity. Now the two quantities are different. Did I not have that? Yeah. So in general, superfluid stiffness is not equal to the condensate fraction or condensate density. In mean field theory, last time we calculated the order parameter psi in the Bose-Hubbard model. In mean field theory, N naught is basically psi square, and rho s is also equal to psi square. So it's only in mean field theory that rho s equals the condensate. But that's not true in general. And let me give you one very nice example. In helium-4, for example, at 0 temperature, right? The condensate fraction is only a tenth of the density of helium, only a tenth, which means in the 0 momentum state, because helium has a hardcore interaction potential, a lot of bosons get scattered out of the k equal to 0 state into higher momenta states. That's what interactions do. K equal to 0 is not a good quantum number once you turn on interactions. So they scatter that single momentum state out of that k equal to 0 state. They get scattered out. So the condensate fraction has been measured by similar neutron scattering experiments in helium-4 and found to be only a tenth of the total density. The superfluid density, on the other hand, at 0 temperature is equal to the total density. All the bosons in helium-4 are able to contribute to this transverse flow and transverse frictionless flow at 0 temperature. So rho s is equal to rho or density, but condensate fraction is different, is less. And in 2D, we saw even a more extreme example in the case of, in 2D, we saw that in the XY model, right, the correlations were always power law. So if the correlation off diagonal long range order doesn't reach a constant, then there is no condensate. And that's what we saw. Even at finite temperatures, I mean, basically, there was power law correlations, except at 0 temperature. At any finite temperature, the correlations were power law, so the condensate fraction was 0, but yet the stiffness was non-zero. That was in the KT transition, right? You all remember that? And then the superfluid stiffness showed a jump at TBKT. So now the two quantities I hope are clear. Let's see, any questions?
Can I ask a question about when you were calculating the correlation function earlier? So how do you know that the like A operator has the same phase at every point?
No, it's not like that is if the system has, it's one has to use the definition correctly. That you're first calculating AR dagger A0, right? You calculate this expectation value. If it goes to a constant, it indicates that there is long range phase coherence because each operator can be written as a magnitude and a phase. And it's only if the phase correlation was a constant that you can actually get this
Okay.
result.
I see. Okay.
I can do a few more steps of algebra in between to show that, but
Gotcha.
you get the argument by, yeah.
Okay.
Yep. I have a question.
Yes.
So, is there a physical reason why superfluid stiffness and superfluid fraction are the same within mean field theory? Because the two seem to be coming from very different physics, but uh, within mean field theory they are the same. So,
Yeah.
like,
Um, You see, mean field theory doesn't include any of the phase fluctuations. So some of the processes that give rise to this difference are not included in mean field theory. I will have to get a little more technical to go into what
okay,
they are, but it's precisely because these fluctuations are ignored.
okay.
Okay. Okay. So now let's come to the experiment to understand why we didn't just see a k equal to 0 peak. So these are cold atom experiments. I have to go into that a little bit. I won't go too much into it, but just enough to make our point. So what you have, let's see, do I have a, yeah. What you have is a trap in which a large number of bosons, these could be some kind of a neutral atom like rubidium. That was the first experiment where this was done. So you put rubidium, about 1 million atoms, and you lower the temperature. Okay, and the way temperature is lowered in these traps, you let the hot, it's like coffee cup cooling. You let the hot atoms evaporate out of the trap, and that cools the trap. Of course, you lose atoms as well, but you are happy with whatever number, like 10 to the 5, which may be left at the end. Okay, so you get sort of a BEC in a trap. Okay, that would have been the end of the story if you just wanted a BEC. This system, if you did do light scattering on this, would indeed produce one sharp peak at k equal to 0. So it would look like kind of the moth with just one blob, except that blob would be very, very sharp. Okay? But now, because they want to be able to tune U and T and make a Hubbard model, right? So they want to make it a tunable system. They now make an optical lattice. So you see this optical lattice, which is superimposed on that trap. And so now they have a periodic potential along with the BEC. And then the procedure, the way they measure N of K, they turn off all of these confining potentials and let the atoms expand. Okay? So, and after it expands, they take this image as I show on the right. They take an image of where the atoms hit at different points. This is a real space image on these gray spots. So they put like a piece of paper or a piece of detector, and they count how many atoms are hitting at different spots. So the darker they are, the more atoms have hit at those spots. And in a way, this real space image can be converted into momenta, because this is something you would have seen if you did some solid state physics, just like light scattering from a crystal. The center spot is k equal to 0, and these other spots are like k equal to 2 pi over the lattice constant, 4 pi over lattice constant, and so on. So these are the reciprocal lattice vectors. Because of the periodicity of the lattice, you get all of these multiple momenta. So that's the picture. Now, what is actually going in? How is the phase coherence coming in? So this picture sort of shows that. Here is the periodic lattice with atoms sitting on that. Each atom can be thought of as a source, like matter waves. And these matter waves expand and they interfere. And that is where whether these points were incoherent or coherent becomes important. So that's the kind of experiment now that is done. And you can see it starts out, this is a time of flight experiment. So the momentum and position get related here just through the velocity. And you get these images. And let me just show you a little more clearly now. So now I'm putting the images on the phase diagram we had. This was mu over u and hopping over u. And I've taken 4 points on this. And there's a beautiful paper from Emmanuel Bloch's group where they can tune the T over U and get these kinds of images. So you have like deep in the superfluid, very sharp peak at the center, and you get these Bragg peaks because of the coherence. They are not all equally sharp. They should have all been equally sharp if there was no Wannier function. There is some envelope because of what is happening locally. There is some Wannier envelope, which I don't need to go into here. But had that not been there, each of these other Bragg peaks would have been equally sharp. Okay. Then you come a little smaller T over U, and you see it is getting a bit fuzzy. And then when you enter the Mott state, all of that structure at momentum equal to 0 is gone. There's a big blob, and the blob gets even broader. So this is a really beautiful experiment. It was never done in materials, helium, and so on. You don't have this kind of control. And this is a really nice example of a totally different system. Atomic physicists only like to study 1 atom, 2 atoms, very high precision experiments. That was their territory. But the dialogue with many body theory made this possible, that many atoms started being experimented with, and they were able to build models because theorists want models. And typically materials don't afford the tunability. So this became a very good synergy for all these 3 communities: the materials, the modelers, and the atomic gas people. Okay, I'm going to stop here for a few minutes, take more questions.
When you said that the Bragg peaks should all be the same size, is that only the 5 in the center, or like every single one?
Oh no, I mean the center one has some intensity, and the intensity in the center is basically proportional to, let's say, like the condensate, N0. These other Bragg peaks, the ones here, which get even fainter, if this Wannier envelope was not there. What is a Wannier envelope? Wannier envelope is coming from just the one body, just coming from the physics of sort of what is happening within a single well. Okay, that's why I don't want to go into it. Like the single atom has some structure, right? So there is also scattering, like, forget any coherence. If you just have a single atom in the path of an X-ray, it will produce some scattering. That's called, like, the atomic wave function will produce some scattered wave function. That will have some envelope. And that's the envelope that reduces the intensity. Okay? But for that, I'm saying all of these Bragg peaks would have counted the intensity to be N0.
Okay.
Any other question? Okay. I'm going to skip this. You can take a look at these slides later. I have tried to make some estimates for, what are, because it's a different system, it's atoms and it's different from crystals. I just wanted to get a sense of what were the length scales. That's something I always do when I'm given a new problem. I always like to get a grip on what are the length scales, energy scales, time scales, all of that. So this was an attempt to do that, and it could be instructive. So just take a quick look at it. I think I was doing this for rubidium. Does it say? Yeah, rubidium 87. And so rubidium has 37 protons and neutrons. So they will always be equal. These are neutral atoms. So the neutrons decide whether it's a boson or a fermion. So there are even number of neutrons here. So this has to be a boson. So, I know that we have some high energy people in our group. So they like to probe at very high energies inside the atom. Then you can't use these arguments. I'm looking at these cold atoms, which are being probed on much larger length scales. So you're not probing inside the atom. So you can give a total statistics to the composite atom. Okay, and then you can estimate the Bohr radius. It's about 1 micron. You can put in the mass. And then if you have, say, 10 to the 5 atoms in the trap, then you can figure out what is the interatomic distance. And that's about 100 nanometers, 1,000 angstroms. So now you can look at what temperature do you need to cool to get a BEC, right? So what you have is a de Broglie wavelength for each atom. And the de Broglie wavelength is h over mkt square root. And so you can write that out. You can figure out, put in the mass, and you get this relation between the de Broglie wavelength and the temperature. And so if you equate the de Broglie wavelength to be the interparticle spacing, that's when the wave functions will start overlapping. Then you get a temperature of about 1 microkelvin. So that gives us some idea about this temperature, because they keep talking about extremely low temperatures. So when an experimentalist says, I have my system at 1 millikelvin or microkelvin, it may sound very cold. But as theorists, we have to understand what is setting the scale and what does cold really mean. So here, what is setting the scale is the de Broglie wavelength and the density. And when you equate these two, you get the degeneracy temperature of 1 microkelvin. So all of this Bose condensation will start to happen below 1 microkelvin. And really, in most of what I'm talking about, these quantum phase transitions, I often just go to 0 temperature. And we have been looking at these interaction effects. But you can also bring in temperature and look at the combined effects of the quantum tuning parameter and the temperature. Okay.
Can I ask a question?
Yes, please.
So we have this Bose-Hubbard model as sort of a effective model to describe this transition from BEC to Mott insulator. But when we are talking about an actual physical system, do we actually think that the terms in this Hamiltonian correspond to physical processes that the atoms effectively go through? Or is this just like...
Oh, no. At that point, it is not an effective description. It's an actual description. Let me go through that, because I may have skipped it, but for your question, but maybe I can go through that. Let me skip this. You all know Bose condensation. Let me just show you.
Okay, so I have a question regarding the phase transition. of the superfluid mod. So it looks like the the Hamiltonian. I mean, if I take the order parameter and write down some kind of a free energy functional on the Mott insulator side, then it looks very much similar to the FIFO theory, because the BI dagger BI will create a grad
Yeah, in
size.
that, okay, okay. Mm-hmm.
And so in FIFO theory, we had this behavior of the critical point depending upon the dimensionality. So D equals to 4 and D greater than 4 and D less than 4. So is there a similar kind of behavior for the Mott insulator phase as well?
Yes, yes. I will come to that. Just wait a bit. It turns out that this model has it has a whole line of, it had, you remember that lobe, right? So it has a phase transition along every point on the lobe, and they can be actually broken into two different universality classes. So wait a bit and I'll come to that. Let me answer Saad's question first on, is there, how do you go from these atoms in a trap and make the model? Is it an effective description? So right here, it's actually a very direct relationship. The effective field theoretic description comes later, but the model actually can be, I should say, constructed directly in this atomic system. So this is one of the very few cases where this can be done. So it may not be a bad idea to get a quick window into it. Okay, so I'm just quick. Have you guys, are you familiar with this BEC and these people getting Nobel Prizes and so on? It's been a very hot field, a cold, hot field. So, think of it, Bose predicted BEC, Bose-Einstein, and Einstein joined that effort by introducing the role of the chemical potential. And this all happened like 70 years back. And, we really didn't have a tunable system. So it's taken 70 years since the first idea from Bose to actually see it. And that happened by these three people. And this is the system being cooled. And this is the BEC we were talking about, with the momentum distribution peaking at k equal to 0. At this point, there was no optical lattice. Okay, so this is Eric Cornell, Ketterle, and Wyman. These are the three people. Okay, so let me see. I may have removed those slides. Okay, give me a second. I think I removed those slides on how to, because just give me a second. I might be able to find it in another place. Okay, otherwise, I'll tell you what, I will post some things on this. Okay. Yeah. Now I remember. I forget my own review articles. That may be a useful way to go. Yeah. Okay. I'll tell you what. Yeah, I found it. So I have posted this online also, and you can take a look at that. These transitions are not the smoothest. I'm sorry. I kind of lose track of where my mouse and things are. Are you guys able to see? No, I think I won't do that because I'm now losing track of that transition. Okay, 1 second. Okay, I will come back to that question later, how you make the model. I've kind of described it in words a few times, but it's essentially done by, producing an optical lattice and controlling the intensity. So let me just say in a few words that essentially by controlling the intensity and the lattice depth, you can control the tunneling, right? Clearly, if the lattice depth is changing, the tunneling of atoms is changing. That's how you can control hopping. And you can also control U, because U is the on-site repulsion. And by controlling the lattice, the well depth again, you can either squeeze the wave function and make it very large. U can be made large or small. So it's a continuously tunable parameter. And in the review article I posted, it's a review article from my group, we have done all the detailed calculations showing how these parameters change as you change the laser intensity. Okay, so let's kind of move from there. And what I want to discuss next is the quantum critical region a little more. So you remember I raised this question in one of our previous discussions, that when you have thermal fluctuations, it leads to a degradation of the order parameter. Your order parameter is reduced. But also when you have quantum fluctuations, the order parameter is reduced. So how can you tell the difference? So today we already saw one very beautiful effect. The BEC that you guys were given, that teaser, is a fluctuating state, right? In terms of configurations, it's a highly fluctuating state. So if you just took snapshots of configurations, you would not be able to tell. You would just see like, okay, I have all the bosons at a site, I have 3 here, 1 here. You will see a lot of these fluctuating configurations. But it's when you do an interference experiment that the phase coherence is revealed. So that's the crucial thing. Quantum fluctuations are coherent. They will lead to interference effects where you can see that coherence. So that's the difference. Now what I want to do, so I hope this part is clear. This is like the single most important message to get through. Okay, now what I want to do is bring in temperature and the tuning parameter and try to understand this quantum critical region. So we have to go away from mean field theory because we have to put in the fluctuations. So I'm going to start, you can see my screen, right? We left off last time with this plot where we had a cut through the phase diagram. This was a cut through the phase diagram. So everybody's on this page, mu over u versus t over u. And let's say I get these Mott lobes and I take a cut like this as a function of mu over u at some fixed hopping. So clearly I'm going to make transitions from a superfluid to a Mott back to a superfluid. And when you have quantum fluctuations, this is the gray plots at the bottom, the mean field are these solid lines, the squares are the quantum Monte Carlo results that include the fluctuations. You can see that the Mott regions, where the superfluid, this is a picture of the superfluid density. So now you all know order parameters, superfluid density, these are different things. And in Monte Carlo, we can calculate both of these separately. So this is now calculating the superfluid density by looking at some transverse responses. By the way, if you guys get interested in these topics, just come and talk to me separately. These are very big topics and they take a long time to explain in detail. But if you are getting interested, you can talk to me later. Here, I want to make sure the big story is getting across. So now the Mott transition is expanding, and I want to now look at what is happening with temperature. Okay, so these are simulations done using a path integral formulation, but not using real space, not using Feynman paths for the complete basis, but using coherent states. And again, I won't describe that right now, but let's assume there's some quantum Monte Carlo algorithm, and this 10 to the 6 got a little bit hidden here, but we actually managed to do 1 million bosons, which was really a big, and in 3 dimensions. It was a very big calculation, but it allowed us to get accurate results as a function of temperature and this T over U. So this is a cut now at some fixed chemical potential, mu over U. So kind of at the tip of that Mott lobe, you're setting the chemical potential there and changing hopping, right? So clearly when the hopping is large, the system is superfluid, and this is showing TC. So how do I get TC? The plot here shows that I get at each value of my hopping and chemical potential, I calculate the superfluid density. And I look and see where does it go to 0. So this is in 3 dimensions, so it's a continuous transition. This is not a KT transition. So I get a continuous transition, it goes to TC. These things seem to have moved a bit. This was TC, and then this is the other TC for another parameter. And you mark these TCs as they decrease and finally vanish at some critical hopping. Okay? And on the Mott side, what is the scale that I'm plotting? What I'm plotting is a gap scale. So on the Mott side, my ground state has broadly 1 boson per site. If I try to add a boson to the system, it costs some energy. That energy is what I'm plotting here. So when the system has 0 hopping, then you basically get a gap scale of order U, right? Now, why is the gap decreasing? As suppose I start from here and I start increasing hopping, why is the gap decreasing? Would anybody like to tell me? That at hopping equal to 0, the gap is on the order of U. That's the energy cost to add an extra boson and make a doubly occupied site, right? Because if you have 1 per site, they are all okay. There's no double occupancy. But if I force another atom on top of it, it costs an energy U. But why does that gap decrease as I come from here with increasing hopping?
The dimensionless variable you're using is T over U, so increasing T would be the same thing as just decreasing U. For
Yeah,
given T over
I
U.
agree, but tell me physically, suppose U is fixed. Why did allowing the boson, so essentially I'm allowing the bosons to hop, right? When it's like a bound defect. And it's again this confined, deconfined kind of transition. So your doubly occupied site is confined, but then as you, so let's say I make a particle hole excitation. Let me not even add a particle. Okay, you can also do particle hole excitation, either way. So what you have are confined doubly occupied sites, and they get less and less confined if the object can hop away. And at some point, there's no string connecting it anymore, and you get a delocalized state, and it becomes a superfluid. Okay, so keep this picture in mind. Now, let's look at the temperature axis. Okay, so what we are seeing is a phase here, which is the Mott insulator, and I have shown a blob and this is actually calculated now from the Monte Carlo. So this is using that n of k with the optical lattice and putting some 1 year, etc. And in the superfluid, you see very sharp peaks and the Bragg peaks. And in the quantum critical region, that's the one I want to come to today. You don't just see something, you see some structure, okay? And you remember when we first started our discussion of quantum phase transitions, I talked about how the thermal fluctuations dominate near the transition. But when you go to temperatures above these scales, there is the quantum critical region. So I want to kind of discuss what is the behavior of these correlations in that quantum critical region. I'm going to show you some numerical results there. Okay, so let's go. Okay. So part of the reason we undertook this is that the experimentalists had this kind of a wrong notion that whenever they saw sharp peaks like this, they would call it a superfluid. And what we wanted to stress was the difference between having sharp peaks like this, which are of order n, okay, meaning you have macroscopic number of bosons in that state, as opposed to something where it may look sharp, but it does not have it's a different singularity. The singularity structure is different. So how to describe that? And that's what I want to do. Okay, so in the simulation now, we can look at a temperature which is 2 times Tc, but close to the critical point. And you can see there is this structure. And now I'm going to take a cut. I basically don't like these kinds of plots, you know, where you have these color plots. I'm not a very big fan of that, because usually these color plots are always hiding useful information. So if you take a cut, then you can see that there is some background, and on top of the background, there is this sharp peak, but it is not really coming from the condensate because there's no condensate here. It is at temperatures twice the Tc, okay? So these are coming from the critical fluctuations of the system, which are controlled by the quantum critical point. Now, you may say, okay, what does the behavior look like if you go below Tc? So let me just sit at the same point and go to a temperature half of Tc. And now you see there's still that background. There's that, you know, peak, there's that feature that we saw before. I've just plotted that in the quantum critical region. But now you see the condensate building up with macroscopic occupation, which is a much, much sharper peak on top of all the previous structure. So this is how you have to analyze the behavior very carefully to distinguish critical fluctuations and long range order. Is everybody good? Is everybody getting this point? Okay, now, so this is, and again, I'm not going into this part in more detail, but you can now start fitting it with exponents and figure out which critical point is controlling your behavior and so on. That gets a little more into exponents and analysis. But rather than doing that, what I will do is give you a physical idea for what are critical, quantum critical fluctuations. I think that'll be more fun. So let me try to do that. Okay, so what I'm doing here is I have temperature on the vertical axis and T over U on the horizontal axis. And I'm drawing this the dotted line as that thermal de Broglie wavelength. When that is equal to n to the minus 1/3, these simulations were in 3D. So when that's equal to the inverse, the interparticle spacing, we define this temperature degeneracy like I talked about. So I'm plotting that dotted line, which is my degeneracy temperature. Okay, and I'm showing that at that point, two bosons are just about starting to exchange. Now we drop, sorry. Okay, now we look at TC, the actual TC where superfluid density builds up. Okay, so for all temperatures above this TC, the superfluid density is 0 and it builds up at TC. So I'm plotting now TC. These are all sketches here, but as I showed you, we have all these numerical simulations for that. Okay, now you see TC is getting suppressed because of strong interactions. That is what is suppressing TC. So what happens, this little cartoon here is supposed to show that below TC, you have all the bosons exchanging. Now, so as you come to a region here where there's some temperature difference between T degeneracy and the actual TC, this is the quantum critical region. I'm calling this a kind of a quasi-condensate. And what do I mean by that? What I mean is that in a true superconductor, you have exchanges of all lengths. Okay, so let me try to explain what that means. So let's say you have n bosons. You will have ring exchanges of these permutations of these bosons, which produce these kinds of ring exchanges on all boson scales, like cycles of length 2, of 4, of length n, all possible length scales. Is everyone understanding what this means, these permutations and cycles? I can explain that later when I go into my notebook. I'll make some pictures. But look at these little cartoons here. It's basically showing that these bosons are all indistinguishable, which means I can exchange a path for boson 1 with boson 2. Boson 1, 2, 3, 4 could undergo a cyclical exchange. That's like 4 particles. In the true condensate, all the ring exchanges on length scales of all the particles are occurring. Okay, but now what happens in this quasi-condensate is essentially you start getting larger and larger ring exchanges, but they are not totally phase coherent. So you may get like a puddle of 4 particle exchanges here, 4 particle exchanges here, but there is incoherence between those different groups of exchanges. And that is why it's not fully phase coherent and there's no stiffness. Stiffness occurs only when there is long range phase coherence. And that happens below TC. So what is basically happening is T degeneracy is not changing, but the coherence, the real long range coherence temperature is getting suppressed, and it's opening this window where you get a kind of a quasi-condensate. So that, I think, might give you some picture of quantum critical region. So just to distinguish, in classical criticality, right, it's you are not getting this kind of structure. Quantum criticality is still building up some coherence on some length scales, which are going to be ultimately diverging as you come here. So clearly, as you hit this critical point, all the length scales will diverge. But here, when they have not diverged, that length scale is indicating the length scale over which you are getting these ring exchanges. So it's a really beautiful picture. And Feynman kind of talks about it in his book. But at that time, neither the simulations nor the systems were there to see these kinds of effects. And so through these path integrals, you can actually make this come alive. Yeah, any questions? These are the actual paths from which you have to disentangle ring exchanges. It's not fun. Taking it away. Okay, so I've distilled a lot of simulation data and made these cartoons, but I like making cartoons because they often capture the pictures very well, but I also like doing the simulations. Then I know I'm not just telling a story. This is the truth. Okay. I think let me skip all this. How are we doing with time? We can take more questions, or this is a problem that you can test so many things, like fluctuation dissipation theorem, which is an important theorem. We talked about it in classical critical phenomena. What happens to those fluctuations in the quantum problem? That's another very useful question to ask. So maybe let me wait and see. Let's take some questions. This is a good time. And again, we can go along the way of making a repository. I have your repository from last time, and I'm going to make short recordings this weekend. But should we do that? Should we just go around, see what kinds of questions people have? Because at this point, there are several things we can do. We can look at fluctuation dissipation theorem in the quantum critical region. We can look at the two kinds of quantum criticality in the Bose-Hubbard model. In the same model, depending on where you cut the transition, there are two kinds of criticality. We can also talk about Higgs modes and Goldstone modes in the Bose-Hubbard model. Believe it or not, there were quite a few surprises even there. Then we can talk about how you develop a phase-only model from here and try to set up some RG for that. So tell me broadly where your interests are. And let's go around the room. Everybody can give some ideas. Okay.
If we're voting, I think I would vote for the...
No, we are not even voting. Just tell me all the things you would like to, and I will, maybe even if we run out of time here, I'll address it later. Just...
I'd like to hear about the different modes.
Okay. Yeah.
Also, maybe more about the stiffness.
More about the stiffness. What about the stiffness?
So you said that you're going to make an effective theory which has stiffness, and then...
Yes. So on the effective theory, yes.
Yeah.
Yes. Okay.
I would like to learn more about the different kinds of criticality that you...
Okay. Yeah. So with these three here, I think, it's my brother. I have to somehow tell him not to call again because I wouldn't know how to turn it off right now. Just give me a second. Yeah, just a second. Teaching. Yeah, you know, my brother is a string theorist, and we've been having very intense discussions on some spin liquid stuff. So he's probably figured something and wants to talk about it. So, yeah. Okay. So let me start with these things on the table. What about some of the other people? What kinds of, what aspects are you interested in? Okay. So be it. No one else has a vote or any specific interest. Okay. What I can do is, so here's what I think logically in the order I will do it is, first let's go back to the Bose-Hubbard model go through the criticality. And then I will discuss the effective theory next time, and the modes, which are really fascinating because there are some gap modes, but the gapless goldstone modes also change near these transitions. Let me see, 340 we have, okay. Yeah, okay. What I'm going to do is, since transitioning between different files is also complicated, let me flash a few things quickly because I have it right here on the fluctuation dissipation theorem. That's another way to see the criticality. And one very important thing is that recently in these cold atom experiments, they can actually do single site imaging. So they can look at, single sites and see if there is a particle there or not. And they can make a whole density map. Then they can change the chemical potential. How do they change it? They just take their trap and they, move the lattice potential a little bit tighter or closer or wider, and that changes the chemical potential. And then dn, d mu, you can look at change in density at a site given some change in chemical potential. So they can really measure local density fluctuations. Okay, so as a result, let me just say what are some things that become possible for us to look at. So the compressibility is a local compressibility, local change of the density in response to some chemical potential change. Okay, so this is a measure of density correlations, not just at a site. That's the first thing to remember. It also measures density fluctuations on distant sites. So it's an operator, it's a response function. Even though you measure it locally, it reflects the correlations which are much more long distance in the system. Okay. And I'm going to normalize kappa, which is this long range, it is a measure of longer range response functions, or you can think of it as a Q equal to 0 response. And I'm going to just normalize it with local on-site number fluctuations. Okay, and I'm calling this a quantity R. And using this R, remarkably, you can start to get a grip on quantum criticality. So do I have a reference here? No, I'll put the reference later. It was done with one of my students some time back. So here is a very interesting plot. So let's say I'm sitting in the superfluid and I'm measuring R, which is, once again, this ratio of kappa over delta n square. And so R inverse, by the fluctuation dissipation theorem, which we have seen, R goes like 1 over temperature. Or, so just keep this somewhere in your notes that R goes like 1 over temperature. The reason is sometimes I will plot R inverse, sometimes I will plot beta, and we will all get confused. So R goes like 1 over temperature, keep that. And so if I plot R inverse versus temperature, it should be linear in temperature. So that's the classical regime. Okay, and you see that at some temperature, these fluctuations stop showing any temperature dependent. So when you see that, it indicates that now the fluctuations are quantum in nature. They are not thermally incoherent any longer, because then it should have had this behavior. Okay, these are things that are worth pondering later, because they are very deep, deep results, I'm telling you, and largely not discussed in the literature. You'll see a lot of words like quantum fluctuations, And within a lot of the field theoretic methods, the way they are accessed is all through exponents. And exponents, in my view, are a very dry way of understanding a phenomena. Okay, they tell you how things diverge, but they don't give you a picture. So what I'm trying to do is to kind of bridge that gap. So I'm giving you some pictures here, but ultimately when we calculate, it will be through these exponents and how they diverge and how they define certain regions. But this is the first, if in any experiment you see some behavior like this, where you had something which was following the temperature and then suddenly it veers off, the first thought is the system disconnected from the fridge. Is Peng Cheng there? Hi, Peng Cheng. Hi, so if you see this behavior, you should not think right away that it is a quantum fluctuation. Theoretically, we will. But if you're an experimentalist, the first thought is my system, am I measuring the temperature that is in equilibrium with the fridge, or has my system disconnected? Once you ascertain that's not the case, then you come to the next exciting possibility that it could be a quantum fluctuation. Okay. And
So, sorry, you're saying that quantum fluctuations don't follow fluctuation dissipation theorem?
yeah, they don't, because that yeah, that's right.
Okay.
They still follow that expression. I mean, that expression is still correct with the t. I'm still plotting the same variables, but the behavior of those variables is such that R inverse, this kappa over delta n square is now temperature independent.
Okay.
Okay, now let me take that same quantity and plot it as a function of beta. I'm just trying to read off certain temperature scales now. So as a function of beta, at large beta, it goes to a constant. And you can read off that peak in that, and that gives you some estimates of temperatures, T star, TC. Again, not to dwell on that too much, but you can start reading off temperature scales from this behavior. When you go to the MOT, then R as a function of beta has a very different behavior. And again, you can analyze these things in more detail. Okay, so I don't want to get too much into this. This is a whole other big discussion on fluctuations and how they don't show the same temperature dependence in quantum systems. And then using just that kind of R object, the compressibility normalized by local fluctuations, you can map out these phase boundaries. And it's rather remarkable. You can map it out from the Monte Carlo using rho s and gaps, and you can map it out using this R quantity, and they pretty much, it's a little different plot. It's beta versus chemical potential tuning with some fixed hopping. I'm cutting the phase diagram in some other way, but you can again see there's a superfluid region, MOT region, superfluid again, and you can get these kind of quantum critical regions. Okay, so that's the story of quantum fluctuations. Now, we can take a short, where are we? Oh my God, it's actually close to the end. But about the two kinds of criticality, that's the next thing I was going to do. I think I won't start it right now. So basically in the next class, I'm going to start reviewing and taking questions. And some of these things that are left, I'll post 3 short videos on criticality, the two kinds of criticality, the modes, and the stiff effective theory. And we'll kind of leave it there. You guys can listen to it and ask more questions. But the next 2 classes will all be about overviews and questions. And even the overview, I will post ahead of time. So it really will be about your questions. So I think this will be a good time to gather our thoughts. And if you feel there's something important you took away, but I didn't bring up in the review, that would be something to absolutely point out. Like something you enjoyed, I talked about, or you have read and I didn't discuss, then do bring it up. So look out for many recordings. I hope I can live up to all that. Okay, guys, more questions?
I have some question about the quantum critical region.
Go ahead.
Okay, so if we go to the quantum critical region, when we try to compute the expectation value of a dagger, that should be 0, right?
Yeah.
So then how can you tell that there's a quantum critical region? Like what quantities can you measure to tell the difference between that of the and a normal state?
Right. So, you know, I showed that n of k.
Uh-huh.
If you analyze n of k, it'll go like 1 over k to the power, let's say 2 minus eta, some exponent there. Okay. So in the superfluid region, you would have a delta function at k equal to 0. In the quantum critical region, there won't be any delta function, but you will get a power law. And the power law will be governed by some exponents, like eta and so on. And these exponents will be those determined by the quantum critical region.
So is it possible that we can measure the entropy to tell the difference? Because they are coherent states. So I think maybe you can measure the entropy to tell the difference between that and the normal state, because I think the entropy will be decreasing until it goes to 0 into normal state.
So say a little more about entropy. What is your idea there?
Because in the low temperature state, I think it's a coherent state. So I think maybe you can measure the quantum entanglement in that, and then when you go to like higher temperature, it goes to normal state. So the like quantum entanglement should goes to 0.
So there are two different things you're talking about. One is quantum entanglement. So, you know, entanglement entropy and thermodynamic entropy, these are two different things, right?
That's right, yeah.
So we have to distinguish these two. So let's say we are at finite, so at 0 temperature, of course, you can still look at quantum phase transitions through the entanglement properties of your wave function, right?
Mm-hmm.
As you go from coherent states to Mott states, you can do that.
Yeah.
Now at finite temperatures, you have to talk about now thermodynamic entropy.
Yes, but I think because you have this quantum critical region, I think somehow the quantum entanglement entropy is still non-zero because you have that like.
So this is actually a very important question. It is still not fully fleshed out how you separate out. So, you know, there was a recent experiment by Greiner in Harvard where they actually took a Bose-Hubbard model. It had a few sites, very few sites, and they managed to measure entanglement entropy. Okay, but that entanglement entropy was at, the system was not at 0 temperature. So that entanglement entropy was actually in some mixed state.
Mm-hmm.
And so this is still an open question. How do you kind of separate out the entanglement entropy of a pure state from the measurements in a mixed state? But in general, your idea is a good one, because you see what is happening. I showed those pictures of entangled, paths, right? In
Mhm.
the normal state, there is no exchange. In the fully ordered state, there are infinitely large ring exchanges. But this state in the critical state does have some entanglement, which reduces its entropy,
Yes.
right? So that's one very interesting thing about thermal fluctuations and quantum fluctuation. Thermal fluctuations always enhance this kind of a entropy. But quantum fluctuations make the system more coherent. So you are touching on a very, like nerve point. And you would expect that your entropy would be reduced because of quantum we call it fluctuations, but these fluctuations lead to coherence. So the entropy would be reduced by this kind of ring exchanges, yeah. Or you can call it entanglement.
Mhm.
Yeah, that's a very profound, very good question. Yeah. Yeah, more questions. That's why I feel giving pictures of what, pictures are really important. You'll carry these pictures with you in a way. All of these exponents are important, but it doesn't match the beauty of these pictures. And yeah, think about it, because this is really what will help me make the effective theory. Whenever people write effective theories, they have deep intuition for what is going on. So the effective theory I will end up writing will be in terms of phases. And it will not be in terms of the phase of each boson that we wrote down. It's an effective theory. So it'll be a cluster of sites that are now assigned some amplitude and a phase. And then we will look at a stiffness between these phase degrees of freedom. That will be some kind of a J. And the effective theory will be an XY model, where J will be the phase stiffness, the superfluid stiffness. That will be one term. But because it is a quantum theory, we need a non-commuting operator, and that will be the density. So it'll be a it'll be a quantum XY model with phases on neighboring sites coupled and a density operator, n square. And n and phi don't commute. So this is kind of where we leave off this course, but it's actually the beginning of a lot of things, including in my own research. A superconductor can be mapped onto this effective theory. So Josephson junctions are described by this phase stiffness, and a lot of things emerge from here. But then you have to root for a second course, and then we can have that discussion. Okay, should we call it a day, or do people have more questions?
Can I ask another question?
Yes, sure.
Um,
If your friends will let you. Okay, make it quick and snappy.
Sorry, so it's still not really clear to me the answer to the question you had asked us earlier, where, like, what experiment should we do to distinguish whether or not we're increasing temperature or quantum fluctuations? Like,
Okay.
is the I mean, I understand that with quantum fluctuations, we're saying that everything remains like coherent, whereas it doesn't do that with thermal fluctuations. But what
So you got the main point. You got the main point.
Okay. Okay.
But if you want more discussions, let's carry on with that. I'll look at people's responses, and we can carry on with that offline.
Okay.
But yeah, it's good to keep mulling over these things. So let's enjoy the day, and we'll catch up next week. Bye.
Bye.
Thank you.
Right.
Oh, Friday, we are meeting on Friday for some mega session. I'll try to see what can be done reasonably.
Okay.
Bye.
Farewell. Stay safe.
Yeah, you too.
I'm sorry, can I ask a question?
Yes.
So the thing is that if we increase the thermal fluctuation, we actually if the thermal fluctuation is very large, we will eventually reach the thermal equilibrium state, right?
Oh, the system is always in thermal equilibrium at every point.
Okay, so in the phase diagram, every point is thermal equilibrium state.
Yeah.
I see. Because I was thinking that there's something called eigenstate thermalization hypothesis, saying that looking at a single eigenstate, you can see that if the system is thermalized or not.
Yeah. No, I'm not in that situation here. We should discuss this, but here every point in the phase diagram is in thermal equilibrium.
Okay, so we don't have
A
to
lot
worry
of
about
that has to do with disorder, and I'm not bringing any of the disorder here.
it. Okay, cool.
Okay.
Okay.
Yeah.
Thank
See you. Anything else?
See you.